Okay, hello. Welcome to the HEIR meeting. Today is the 12th, not the 15th. So we had 55 PRs merged since last month. My personal pride is in getting this packing pipeline PR finally merged. It's been too long, but it involved a bunch of helper PRs along the way. So I think the biggest one was that the client helpers are now created um, above the scheme level. They were previously created at the LWE level, and now they're created at the secret level because they're needed to describe the packing that needs to happen before encryption. That created a bunch of issues with, since we don't have an encrypt op at that step, now we need to do secret conceal, and then there were various lowering issues with secret conceal and various analysis issues. And so one of the bigger things that came out of that is that I basically redid a bunch of the analysis infrastructure in the code base. And a lot of this was based around secret generic, which now implements region branch up interface, and that makes it so that analyses don't need to special case on secret generic. So it will just like make things work. But then there were some like slight changes from that PR that you may be interested in. There were also some like a lot of changes to emitters, and there was one like kind of meaningful Latigo bug that was me not understanding how Latigo works. But yeah, so all of those, there's a lot of work that went on. That packing pipeline is now merged, yeah, the next step to this whole thing I'll discuss later down the line. There was also a bunch of work on the Python front end. So now the Python front end has some kind of support for CGGI. The thing that's missing, so you can write programs, compile them with CGGI, and you'll get CGGI dialect IR as output, and then it will say, sorry, can't go any further. That's because we don't have a supported backend that works both with HEIR and with the front end. The front end only has OpenFHE. Our CGGI backends only have TFHE REST or JAX-site. So if someone wants to add the OpenFHE, BinFHE backend, then we can have end-to-end Python front end with CGGI. Otherwise, I guess it's either adding OpenFHE, BinFHE backend, which would work with our existing compiler, or adding support for a new backend language in the Python front end, which is a lot more work, in my view. There's also the tensor support typing PR got merged. Alex has been doing a lot of cleanup and casting between MLAR types, which is needed for CGGI because we need like binary bits. You know, if you're doing like Boolean operations, those need to be represented properly in the type system. Okay, so Asra has been working on this ambitious idea of removing the need for bufferization in the CGGI pipeline. So we used to have to bufferize to memrefs and then deal with Verilog at the memref level, and there was like a bunch of issues with that because, yeah, okay, I won't go into too many details. I think, Asra, you have it basically working. I'm not sure if all the PRs are in yet.
Yeah, there's one PR I am prepping right now in terms of testing. We have to add in some support for cleaning up a tensor semantic program into the circuit representation. So we have an upstream pass, well, no, like an HEIR upstream pass called forward insert to extract. So I'm adding some functionality to that to like traverse over the insertions properly. So you'll see that PR today, and then you'll see the moving over of Yosis after that's merged.
Got it. Okay, so this is on the way. Okay, and then next, so I did some work on the macOS build. I got fed up with fielding questions about macOS build breaking, not just from Mark, but from my manager at Google as well was trying this and had all these problems. So yeah, so now I found basically that a bunch of the dependencies that we're breaking are now available on the Bazel Central Registry. There's a lot we can migrate, though not all of Yosis can be up there yet. But then some of them that had problems, I was able to figure out how to patch the Bazel registry with local fixes so that things build properly. And then I upstream some of them to the individual project. So Soplex now has it, and when that trickles through, then we'll be able to remove those patches. But now if you have macOS build questions, It should build, and you can yell at me, and I'll probably be able to fix it faster from now on. Okay, so so after this packing pipeline got merged, one of our big efforts is to get some ML models actually smoothly going through the whole pipeline. At the front end of that, there's our torch to lineage export that gives you a bunch of messy lineage ops that aren't doing things very smartly. So we have a whole list of canonicalizations that we're adding that will basically simplify that IR to make it compatible with like our packing pipeline. Like an example is if you do a transpose and then a mat vec, you can just do a vec mat, and the transpose would be an expensive operation in FHE. Okay, so then there's a host of other PRs that went in. So we have the LW dialect now has RLWE ciphertext plaintext ops. There's a new pass called CGI decomposed operations that is supposed to bridge the high-level CGI API with the lower-level like programmable bootstrap. So I think there's still some missing pieces to that. But like for example, if you have I think like a 4-bit add or something, that can be broken down into PBS now, or sorry, no, well, it's the
It can
bitwise
be,
op.
but that's height.
Okay, that's not in there. Okay, sure, but so there's some new pass here for connecting the higher level and lower level parts of the CGI API, and then there's support for the TFHE REST high level API, getting more bitwise ops. That's for the FPGA stuff. There's a tensor to scalars pass that now supports ND tensors. Okay, so I have this little tool called lit to Bazel that you can give it a lit test file and it will give you the Bazel invocation you need to run it. I got tired of copying and pasting that and hitting enter, so I added a run option to the script so it will just run it right away and add some extra helpful debug flags. And now you can give it a Bazel target instead of just a file path, and it will work as well. So if you go from Bazel test blah and it fails, then you can just replace Bazel test with this script and it will still work. Let's see. What happened here? Oh, I think we fixed a couple of small bugs, old bugs with secret generic. There were some. We stopped it from changing function signature types when you were collapsing a plain text op, and instead used secret conceal to maintain the integrity of the type system. And then there was some. I think conceal op lowerings was something that I had for my packing pipeline. But yeah, so there are changes to secret generic canonicalization. We had a PR that would take a function argument that is immediately layout converted and then hoist the conversion directly into the layout attribute so that it can be put in the client helper. There was an upstream bug that got fixed that made it so that our NTT lowering was invalid because it was using affine 4 with a iter arg as the loop bound. And so I just changed it to use SCF4 and now everything was fine. Okay, there was another old bug with forget secrets. I think when we wanted to use the Yosis pipeline and get down to CGGI, or before CGGI to before scheme to CGGI, we wanted to test that the Yosis output was correct by forgetting secrets, lowering to LVM and running it. And that was broken because you couldn't lower secret cast. And so I added a lowering for secret cast. Hongren found a bug in optimized relinearization that was not respecting the max dimension constraint. And so I've realized I just had it off by one error, and I fixed that. Yeah, secret distribute. I got tired of working on packing stuff, so I took a break to fix old bugs. And so this was a bug from like 2 years ago where if you tried to do a secret distribute generic and your secret yielded the operand twice, like if you did some operation and then yielded to the same value twice, which was a natural thing that came up in some case, then it would just crash. And so I had support for that. And then we have a PR that sort of formalizes the difference between the extended encryption technique and the standard, I think it's called hybrid encryption technique for OpenFHE. So that's now on the scheme parameter and threaded through properly. Okay, so in progress PRs. So there's a couple of improvements to the layout pipeline that handle the ops that are coming out of Torch. So there's expand and collapse shape that is supported in layout propagation, and layout optimization also I think now supports expand and collapse shape. But the main thing that is working on right now is formalizing the how do you hoist something when the kernel will change or when the packing will change as a consequence. So like for matrix vector multiplication, that's like the hard one because the vector packing doesn't change, but if you are hoisting a layout conversion, then the matrix packing needs to change. So there, I wanted to clean this up a little bit, so I added an op interface that says, okay, here's all the information that an op needs to provide for how you can potentially hoist a layout conversion, and there's some like formalization of like what the kernel is and how things change. That I think is the infrastructure is ready to go in. I haven't yet tackled the actual details of like the harder kernels there. There's a design doc for noise analysis in which Hongren wants everyone to be very clear that we don't guarantee the security and correctness of the noise analyses because they're all sort of active research. Okay, so there was a couple of PRs in which people were doing things like the simplest one is the where is it? Yes, down here, the polynomial Chebyshev lowering. So in that case, the Chebyshev lowering comes up with an arithmetic tree of operations and then materializes that to the IR by calling create op. The way that the collaborator was doing it was not separating these two steps, and the code was just very messy. And so I said, okay, why don't we just like make a proper data structure for a tree of arithmetic ops where the leaves are constants or SSA values. So I made that data structure, and I think that with some slight modifications, it can also support a couple of other things where we have the operation rebalancer. So we could add rebalancing logic explicitly on the tree instead of doing it how we do it now, which is a little, I thought it was a little confusing. And then I think Hongren also has a PR that is about doing symbolic noise analysis, where instead of just tracking a single value, you track the entire symbolic expression, and then you can evaluate it. I don't remember exactly what the nice thing about that is, but I think you can evaluate it more. Maybe you can simplify some of the bounds so it's not as loose if you see the whole expression. But in that case, also, I was like, my main criticism of the design there was that like, okay, we should like properly denote the tree of operations as a data structure rather than I think it was another sort of like ad hoc data structure in there. It's like, okay, let's centralize all this into one thing. Yeah, criticisms of this are open. Please talk to me about it if you're interested. Okay, so there's also a couple of, this was back to my cleaning up some issues that I discovered during the packing pipeline. Dimension analysis is now going to be back propagated to the management init ops so that if we need to encode plain texts that are compatible with ciphertext at like a higher dimension, like if we're doing lazy relinearization, then we'll have the information that we need to do that. Okay, this is Hongren's symbolic noise analysis PR. I also tried updating OpenFHE to version 1.3. So this is actually working. I have the internal patch done. The problem is that there's one CKKS test that's failing, and it's a test that has no moles in it. And so I noticed that the crypto parameters are setting multiplicative depth of 0, and it seems that that may be the source of the problem, that logic has changed in version 1.3, because when I change it to set multiplicative depth of 1, it works. And I remember there being a discussion about this earlier, and I think Hongren had looked into it, or Alex maybe. I don't know if there's any thoughts about like what the proper fix for this is.
You set it to 1 is what I think we came up with, because I ran into this when doing something in the front end, and it turned out that I think what we have now, Hongren, if I remember correctly, the fix is just in the backend, we set it to like max of depth 1. So I'm surprised that you see here choose a multiplicative depth of 0, because I think the fix that Hongren did was just setting it to max computed depth 1.
So okay, I mean, that was basically what I thought I would do, is just like if it's 0, set it to 1. Okay, so I'll go ahead and do that. Okay, so the next thing we have what is this? Oh, I had a PR to support a secret conceal as like of a plain text as a trivial encryption in the noise analysis. That PR is mildly blocked because there's no trivial encrypt op in the actual lowerings, like in the backends. So there is one in all the CGGI backends we have, but there's not one in OpenFHE and Latigo, I don't think. And so what I was thinking I would do to fix this is to just like later match on trivial encryption applied to secret ciphertext op, and then just collapse that to a ciphertext plaintext op.
I think there might not be an API for it, but it might be a constructor on the ciphertext class.
Okay.
So right, because you don't need any of the actual like context information for this one, you just give it a polynomial. So I think there should be a way to do this.
Why do you why does it not become constructing a plain text? Is it because it's a secret type that gets translated to a ciphertext type?
I think the main thing that I think this was in follow-up with the desire to have like a type, like if we need to reconcile types at the high level by like, if we need to like peel the first thing off of a for loop because the first thing is a plain text, right?
Okay,
Then
yeah. So
we need to do a secret conceal. So it has to be ciphertext type, even though eventually we don't want it to be. And then we do the noise analysis on that IR before we lower it to scheme.
But peeling it would be a result of a ciphertext after the plaintext like ciphertext op, right? It's not a trivial encrypt. It's like you're peeling off the first iteration.
Oh, that's true. I mean, like I didn't have like an exact example that came up with this. I just thought like, okay, it would be like as I was going through the improvements to the like noise analysis at the secret level, I was like, okay, it should just support all secret ops. And this was like, I think the last one that's not fully supporting. And so I was like, okay, should I do something for this? And then it seemed like it might fit in with that like type reconciliation. So I left it as a draft because I'm like, okay, I'm not sure if it's worth putting in all the effort to finish this unless like we actually have a concrete use case for it. So I'll probably just leave it in a draft for a while until a problem comes up. Okay, and then our internal collaborator Vadim is still working on the polynomial eval Chebyshev lowering. I might end up picking that up because it's going to become a blocker for us once Oscar and I get this like machine learning model through the rest of the pipeline. So yeah, I might take that over at some point. Okay, yeah. So notable new issues: we want to get an MNIST model from PyTorch directly into HEIR and going to a backend. Once this is done, I think the only thing stopping us from doing other machine learning models will be kernels for other operations like convolution that we don't have. And then, yeah, okay, so yeah, I talked about CGI decompose operations. I think that PR has a list of the remaining ops that are needed for that. There was an interesting paper that I found from Tobias Grosser's group on using eGraphs in MLIR. And they do a bunch of things that can only be done in XDSL, unfortunately. But the idea of using eGraphs for holistic kernel selection seemed like a cool idea to me. So I filed that issue as a backlog to try that. Hongren mentioned a new FHE backend for BGV and BFE that seems to be a modern version of HELib. It has a bunch of the like HELib only techniques that got ported to it. And so he likes the noise analysis in there, and it might be interesting to have as a new backend. And then I think this issue was filed by Alex about the improved support for floating fixed point data types in the front end. Other than that, it's not been a lot of new issues. Okay, so I can open the floor to any topics people want to discuss. If there's nothing else to discuss, then I have some complaints about the layout work that I've done that are showing up as we're trying to push this model through. So I have some thoughts about like what we can do to improve that. But I will first start by open the floor to anyone with topics they want to discuss.
Yeah, maybe on the floating fixed point data type thing, I guess we have support in some sense for some of this, but it's mostly my question is about what are the semantics that and the knobs that people want to be able to twist, right? So one of the issues is that with the integer types, it's relatively easy to tell here how many bits of precision you want when you're using them, right? Definitely for the CGTI schemes, there's a very clear translation between you giving an I4, I8, whatever type, and the same is sort of true for the arithmetic, precise schemes. However, for CKKS, this becomes much harder, right? And I guess it's like both for the front end and I guess also if you're writing your MLIR by hand, right? You get these MLIR types, I4, I8, whatever, and you can use them for the integer things. But for the floating point types, whether you give us an F32 or an F64 doesn't really give us any useful information on what are the input ranges that you expect here, what are the scales that are appropriate for this, and what is the precision that you want out at the end, right? And so I think one of the reasons why I'm bringing it up here is because I guess we have a few more people here. Do people have any use case where they already know how they want to do this? Is this something that you want to be able to specify, or are you fine with having the compiler figure this out somehow, which isn't necessarily possible, right? But yeah, so this is I think my main question, both for potential users here, but also for us, I guess, as how are we going forward with thinking about especially I guess CKKS semantics, right? Because this also impacts our internal passes and optimization, right? Certain rewrites might or might not be legal under a certain precision requirement, for example, right? And so, yeah, I think we don't really have any system for this at the moment. And so in some sense, we don't have any technical debt, which is nice, but it also means we don't really have an obvious first step.
That is true. Yeah, we had talked about running it, right, and getting runtime information, at least for machine learning models, and then ingesting that back into the compiler in a second pass. But yeah, I don't know. I don't have any strong opinions about how we would have the user specify it with a hard override.
I think one of the things I would probably postulate as a reasonable first design is that we assume that for each input value into the computation, we know the scale and precision that's intended, right? Which is maybe not something you want to actually ask the user for. Maybe the information the user provides needs to be somewhat converted into that. But I think for the actual lower level compiler parts, I think it's a reasonable assumption that we need this in order to be able to do anything useful, right? Because I think if you don't have that, it becomes very difficult. Otherwise, we might have to back propagate or something like that.
I'm just trying to get my head wrapped around this, but why are the standard IEEE floating point data types not sufficient enough?
Oh, right, because with CKKS, you will never be able to have that much precision as even I guess a float 16, right? CKKS will it will probably not be able to capture them precisely. And then there's also the problem that with CKKS, you have, in addition to the precision, which is just how many bits, right? You also have the scale as a parameter that you need to set. And so there, yeah, there is sort of even an F16, if you were there's a million different CKKS parameterizations that would be a reasonable interpretation of that. Yeah.
I think before talking about the precision, we need to have a range analysis first. So just the worst case analysis, and then later we can do some user annotation. But before that, we have a worst case one.
I think there's some kind of profile guided quantization that's popular in the ML community. So maybe, if those passes are available for the program from plain text, you can, they could. So there's a, kind of a profile guided quantization passes maybe available in the machine learning frameworks or, passes that can be, sort of passed from the plain text range analysis into the ciphertext. That could be useful. I think it kind of models your support for polynomial approximations and things like that.
Yeah, I've linked an issue in there where I sort of explored some of the tools available for doing this, and then I have another. What is it? I wanted to go specifically to like Torch. Oh, whoops, that's not the right one.
Okay. Yeah, thank you.
Hold on.
Yeah, I think for machine learning stuff, I think the best case for the compiler is if you pre-quantize before hitting our compiler, right? So that by the time it hits here, it's all int 8 or whatever. But that actually introduces a new fun challenge, which is that currently the way HEIR is supposed to work is that it guarantees that if you give us an int 8, you will get int 8 semantics out of the output. And I'm guessing we technically fulfill this promise right now, because if you have an int 8 and you try and do CKKS, I think it just crashes or gives you an error message. But I guess we want eventually what we want to be able to do is take a pre-quantized machine learning model that's at I4, I8, I whatever level, and run it with CKKS. But then we need to have some sort of way to say this is fine to do, right? We don't need precise integer semantics here. We're fine with approximate like CKKS error at least. Because I think that's what most people seem to be doing right now, is they do some kind of maybe FHE aware, but maybe just sort of standard ML quantization. And then they still use CKKS in order to get the rescale and the fixed point blow up, like to avoid the fixed point blow up that you would get with another scheme.
I have not came across a lot of ML CKKS papers that does quantization. So I think most of them will do just some post-training quantization. So basically just train network, fix it to the correct quantization of CKKS. But like quantization aware training for CKKS, I have not seen it across. So I really think that the quantization errors are so slow that the network can just absorb them without any big troubles.
Yeah, I think honestly the biggest one here is, I think that's a good point. If you have a like fairly small model in some sense, right, or like fairly quantized model already, then it's fine. And also if you quantize to CKKS, what a lot of people do, for example, is they assume that the scaling values that you use, like they're definitely not homogeneous across like the model, and they usually assume that it's fine to leak those, for example, or at least fine to not specifically protect them. So there's some like challenges here about like what exactly we want to offer in terms of like, the protection for the model, etc. But yes, that's a good point. A lot of people just use a like normal model and then do some like mapping to CKKS world. But I think that then like brings us back to like the input is floating point. How do we translate it problem, right? Mm. I have seen some works that do like really heavy quantization just in the machine learning world and then do, but you're right. Increasingly, people are just using models straight from Hugging Face.
But like those very heavy quantization is always for the CGI world, where you only got like 3 or 4 bits or 2 bits in Zama's preferred case for each weight. And
yeah, I mean, like when I say heavy, I still mean like I8, I16, right? Like it's not like
that's the hardware quantization. So that's really for putting it, or that was like 5 years ago to put it on the chips, because the chips was at that point only be able to do I8 arithmetic.
But yeah, I think my point is basically how do we express the acceptable losses here, right? And I agree with Hongren that like one of the first things we need to do is to have a range analysis, and then probably some way to hint at certain points in the program where the range analysis just goes like top bottom, right? It just gives you nothing. We have to give a way to hint that after certain, let's say, layers, for example, after like a layer norm or something, we expect things to be with high probability in certain ranges again. I don't think that any of the machine learning works that are out there right now are doing this in any sort of systematic way. It seems to be very much sort of like a hand glued together / hand coded approach, where they just have a polynomial approximation that works, right? And mostly, I think that's like due to experimentation and empirical validation.
I was quite a bit concerned about the security implication of empirical methods, because you can always construct a worst case intermediate value, and that will break the security. So
yeah, I mean, I agree. I think the people that are running things like GPT and Llama 7B probably aren't willing to take the performance hit though to make it like fully secure, which is, you know, but I guess that's the point. Like, do we want to take a stronger stance here with the compiler than maybe some of the like more practical works?
I mean, I think in the end, we're going to allow people to override the compiler in arbitrary ways, right? So I don't think we can guarantee anything about security, especially if we're allowing the user to like annotate intermediate steps of the program with like, okay, here's what I want here. Okay. I mean, I can also talk about this layout attribute thing. So we were looking at sort of our layout attribute as like this affine map that maps from data entries to ciphertext slots, along with this sort of weird alignment attribute that I added to support the concept of padding and replication. And this is kind of weird because the affine map is like a function from the domain of the data indices to the domain of the slot indices. And this function is, when we materialize this function, it's like you iterate over the domain, you apply the packing, and you get something in the codomain. And that doesn't always fill up the ciphertext, especially if you want replication. It's not going to fill up the ciphertext. And so the alignment was sort of compensating for that in an unnatural way. And I was thinking, okay, maybe it would be better if we went the other way and mapped from ciphertext slots back to data slots. And that has, some of the formulas are simpler if you do that, but then we realized that there are also examples for which that doesn't make any sense, for kind of the same reasons, just in the other direction. And so we were thinking about it, and I think that it also came to a head when we're trying to hoist a layout conversion through a matvec, because when you hoist a layout conversion through a matvec, basically you're saying, okay, the vector packing looks like this, and then after my matrix vector multiplication, I want to change the vector packing to be something different for the next operation. And you want to try and hoist that up through the matrix vector multiplication so that you don't have to do the layout conversion anymore. And that's fine for the vector. The vector is invariant, layout is invariant for all of the matvec kernels. But the matrix needs to be changed somehow. So like if your layout conversion is like rotating the elements of your data vector, right, in their packing, then you need to affect it, like for like the Halevi-Shoup kernel, you need to then swap the order of the ciphertexts that you pack the diagonals into. And then there's other, like if you do striding, you have to do something different. And we sort of realized that in order to do this, you kind of need to be able to invert affine maps. And there is no way to invert affine maps. In general, it's not possible because they're not necessarily invertible functions. And practically, there's no inverse, like attempted inverse function upstream that would even try to do this. And then even if you could do that, the alignment attribute, it just like throws a wrench into things, because it's like, okay, if you change from replicating to zero padding, like you just have to have a bunch of special cases in there that are really annoying. And so the idea that we came up with that was kind of inspired by what also exists upstream is to generalize the concept of packing from like a one-way mapping to just an integer relation. So you would say, okay, the integer relation is the set of pairs of data slot indices and ciphertext slot indices that satisfy a list of semi-affine equations. And this allows you to use all the simple formulas that we normally have to express whichever direction of relation you want, from ciphertext slots to data slots or vice versa. Both of those are valid. And then you also can do this hoisting easier because composing two integer relations is simpler in a sense. You don't need to invert anything. You just, like, okay, getting too much into the weeds, but you sort of add an existential quantifier that says, okay, the inner relation that connects these two things, there exists a way to go backwards from this and to this, and then you can basically write this down. So basically, if you have support for a set of tuples, or integer relation is a set of tuples that satisfies semi-affine or quasi-affine equations with existential quantifiers. So if you have that, then you can represent sort of everything that we've tried to represent. So everything we had before, including striding and padding, in addition to like making this hoisting a bit simpler. So we were thinking that we could, I haven't had a chance to like sit down and really prototype this out in the code yet. I was just doing everything on paper to convince myself that it made sense. But the nice thing is that HEIR upstream has the concept of an integer relation, which does lists of quasi-affine formulas with existential quantifiers. So that's all there. And it also has a compose operation that allows you to like connect to, like, a layout conversion would be basically the composition of two layouts. So it seems like there's a lot of infrastructure upstream already. It doesn't seem like it's complete. So I think some of this like doesn't support modulus as an operation, but does support div mod as an operation. But then we were thinking about it, and maybe you can support modulus by just adding an extra index in there that corresponds to like the divisor that you are doing your modulus with respect. So they call that flattening, like flattening the modulus to like just adding an extra quantifier. So we're thinking that might work. But then I think this, without this, it seems like this is going to be just a lot more painful than it needs to be. And then the nice thing also about this is that all of this integer relation stuff is implicit. So once we have like our integer relations represented throughout our program as packing, the only thing that you need to do when you're materializing it to like actual packing code is to just iterate over the space and just check each quasi-affine thing, and if it's correct, if it results in something that's satisfied, then you can do the mapping from data slot to ciphertext slot. So I don't think that, like, it's not like we need to do some complicated solver analysis to make sure that I mean, we could do that, right? If you wanted to have like a packing system that was able to like analyze these integer relations across like multiple things and like come up with a real, that's what they do for like tiling, loop tiling and loop fusion and stuff with these interrelations. Upstream is they run some Gaussian elimination basically that figures out like a different ordering for things, and then materializes the solution to that to like a new for loop. So we could try, I don't know how that would work for packings, but even if we don't do that, I think the infrastructure of having these concepts would I think make this a lot simpler, and reduce a lot of the complexity that comes in through the desire to do padding and striding and replication and stuff. So that's sort of where we're at with that. And if anyone wants to chat with me more about that, I'd be happy to. I think I would love to talk with like Edward. I don't see him in this meeting, but he has a lot of practice with packings, and so I'd love to hear his thoughts on this. But yeah, so that's where that's at right now. And it's kind of blocking us getting MNIST through the pipeline. So like I will probably be spending the rest of the week like prototyping this, and then if things go well, then I'll be porting it to HEIR next week.
How scalable is this, right? Because I think right now we're looking at very small matrices, especially MNIST is tiny, right? But like if you want to make HEIR eventually do things like Llama 7b, I think we're looking at like, matrices in the tens to hundreds of thousands of elements per dimension, right? So is that something that like upstream they're already doing this to that kind of size tensor?
So most of the it scales poorly with the number of dimensions, not with the size of each dimension. And so they will, yeah, that's like one constraint per dimension is usually how it goes, and then the values end up being coefficients in like some matrix. So if you want to do an analysis, there's that. The materialization of the right, we would have to. The weird thing is that we wouldn't want to unroll those loops, obviously, but that would produce a nested loop that iterates over all the dimensions in order to actually assign the packing, which is, I think, required. We need to do that anyway. So, okay, yeah, actually go ahead, Wazoo, why don't you preempt my discussion and let's talk about Kornami stuff, because I want to hear about Kornami.
I'm just like putting it out there. I can join the call on my way, but I just wanted to add the links because I can't type when I'm driving. Yeah, I don't mean to interrupt your call. Yeah,
the first one also
No,
came up once or twice anyway. I guess like we didn't put this on our agenda today, but we were talking about program segmentation anyway recently, and I know that that's probably a topic of interest to Alex as well, and so we meant to have.
okay. Yeah, I think as per Alex's comment on the Discord, I asked on the LLVM, the MLIR channels, and they recommended the using of this GPU outlining pass, and I think with some study that can be grafted into this program segmentation for exit dialect. I think maybe it is after some work at Kornami side, I think there is some generic concepts that can be used for any accelerator, and we can add that as a generic backend, and the outline, the program segmentation will be useful in that sense.
Yeah.
And then the second one is, I've been following this SIM FHE project from Boston University. So a slightly like a different side of things. So it's they're doing estimations for CKKS, and this team's work is now, I think they're able to work with. They have custom FPGA solutions for running FHE, and they're able to publish some benchmarks recently with the AMD hardware. I'll drop the link on the Discord later. So yeah, I think that's where this is some of the preliminary work, and that kind of ties into the sort of noise analysis / resource JIRAs that you have. So yeah, those are the two things I wanted to add today.
So the purpose of the program segmentation is for multi-device? Is that?
No, just offloading to a device. So because the Kornami device is a systolic array, so we would like to we have a benefit of doing, we have the benefit of having pipeline parallelism, whereas more typical GPU like OpenCL like devices, they have to do kernel launch for every operator. So there's some flavors there for the backends, but sort of a generic segmented backend dialect would at least provide some passes, and then the downstream exit dialects can use that.
Yeah,
so
I think
go ahead. Yeah.
For Heracles, it's different reasons, but you also want a batch. You want like a little batch of operations, ideally with great memory locality, for example, right? So I think the interesting thing is, first of all, yes, I think picking like the same segmentation operation, like the same region bearing op for everybody to use, is obviously a great benefit, because it means we can build like infrastructure on top of that, rather than everybody having like Konami.segment, Intel.segment, whatever dialects. And then I think the other one is that we might even, I don't know, but this might even be something we can reuse for like program segmentation for like scheme switching or something, right? If it purely means sort of like this chunk is like execute this together, right? Is sort of the meaning that I'm expecting this operation will have. And so, yeah. I also looked at because I recommended to Foundation, hey, there's probably an upstream op to do this. And yes, there is like GPU.launch and the like other things from the GPU dialect, but I'm not sure if that's like exactly what we want to use. So I think that's probably the first open question is whether we want to adopt the upstream GPU dialect stuff for this, or whether we want to roll our own if we have some other requirements. I think I'm open to either. I just don't know enough yet about the GPU dialect to know if it has any limitations that we don't want.
Yeah, I feel like it would be nice to have like I don't know, maybe Alex, if you and Mutu could have like an example that like demonstrates some of the requirements, and then we could go from there.
Yeah, I can post some content, like a small one-page kind of write-up for that. Yes,
Cool.
thank you.
I haven't seen this sim FHE either.
Could we just use it as a backend, or is that like, does it not work that way?
No. I think Konami, we are about to release some work at the NIST conference, upcoming conference on resource estimation. So essentially, I think the crux of the idea is you can walk the IRs as converted into ciphertext from HEIR. The plain text program can convert ciphertext, and then we kind of estimate how much hardware resources are needed to evaluate those programs. So that's what the sim FHE does, and they're like for any compiler, you would need to estimate the resources. So that's where it comes from. And this project from BU, they kind of they use it for FPGA compilation as a pre-processing steps for CKKS especially. Yeah.
No, I mean, my point is, if we technically can integrate this into HEIR rather than by re-implementing their work, so by just making it like a back end, obviously.
I see. Okay.
Because they seem to have like evaluate Pi, they seem to have like the whole list of CKKS operations that we would want. So maybe we can just do a really quick like pass that goes from CKKS dialect to sim FHE, and then you sort of get this from HEIR without having to re-implement their logic.
I see. Okay, you just like kind of run a Python tool and stuff like that. Okay.
Yeah, we can just the same way we emit like
the Yoast
code, right? You just emit Python, right?
Yeah, of course. Yeah, I think we should definitely explore the path of least distance and effort, and also to least duplication, because clearly, I know my limitations on this side with maintaining, not a cryptographer. So that's cool. That's useful input. Yeah, thanks, Alex.
Yeah, it seems pretty simple. Sorry, I'm just browsing their API in a different tab. But okay, cool. We got 10 minutes if there's any other topics people want to discuss. I see new faces, new names that I don't recognize. How about Alex? I put on hold actually distributing the front end on PyPI. I don't know how you feel about this, or if you think I should finish that. It's pretty easy at this point. You just need to set up a workflow and get like the credentials and stuff for the PyPI account.
I think my opinion is that we have 30 days to make this a thing, right? Because
30 days.
Well, FHE at PDX would be in 30-something days. So I think that's my.
We want to pip install it by then. Okay.
Like my point is, take all the time you want, as long as it's less than 30 days. Because I think that would be really cool to have it be pipeline distributable by the FHEIR PDX event, right? Because getting it to run for people without that, I think, would be challenging.
I thought since it's more of a hackathon that we would need people to build it from source anyway. But
I think at least, like, I want people to at least be able to play with it, because I think there's a lot you can do with just access to the like compiled binary already, right?
Mm-hmm.
Figuring out where it breaks, how it breaks, pipelines, etc. Right? So yeah, I think I agree. For the hackathon, hopefully, ideally, people are willing to pre-install it and have it like run from source. But I think, yeah, having it there for the people that maybe want to play with it but don't want to work on it, right? Because I think right now, everybody who uses HEIR also works on HEIR, right? And I want that, like, I want those two sets to start diverging.
Okay. All right, go ahead, HK.
Yeah, I have a question. So I'm new to the meeting. It's very simple. What kind of debug or profiling tools do you use in general when working on this compiler stuff? Because I find like we're going from one pass to another, and it can be pretty intense sometimes when there is a large graph.
I guess the question is, do you mean profiling and debugging the compiler itself or the resulting program that the compiler produces?
Well, the resulting program is specific for the hardware, right? So not the
Right.
profiling and not the profiling and debugging the resulting program, but like kind of when we are building a compiler, like if something is going wrong, like are there any tools or visualization stuff that we use to debug the compiler itself?
So we don't have anything custom for our compiler. We just have all of the existing upstream tools. So like there's there's a flag called MLIR timing that will give you like a timing breakdown per pass. That's useful if they're finding like bottlenecks. There's a bunch of debug and debug only that will like print out useful debug statements. And then there is things like MLIR print IR after all, or MLIR print IR tree dir. And that will basically, after every single pass, it will dump the IR to a directory with the name of the pass that just ran as like the file name. So you could use, I use this a lot to like create a minimal reproducer of the problem I'm facing. It's like run the compiler until it gets to the pass that something bad happens, extract the IR from that step, and then I can like work, iterate more quickly on that. Yeah, so there's this debugging page, and then there's also
just for like posterity notes that you should maybe like annotate. You can only run the debug and debug only pass if you build in -c debug.
Okay.
So that sometimes will trip people up of like, why is that not working? And then also
it's
like
the default
MLIR
in our Bazel RC, but yeah.
So these are mostly like print-based debug, or they're more like
this one is
okay.
all print-based debug.
Okay.
Yeah. So I think there's also some tools that will give you like a visualization of the compiler pipeline.
Yes.
I think Alex has a lot of experience with those, maybe.
Yeah, you can look at like how the front end does this. I think it's maybe one of the easiest ways to do this, but there is basically a graph vis output that you can get from the IR at any given point. There is a command, I'm sure it's on that debugging page that we linked, to basically get a dot file that you can then look at with any graph vis thing. They're not the most helpful for large IRs, but if you have small IRs with non-trivial like arithmetic operation like trees, it's very useful. The other thing is that, like, I know Jeremy doesn't believe in like attaching a debugger to HEIR opt, but I have actually had some.
You can use LLDB. I've also done it, but I found it's difficult to get it to work with Bazel.
Right. Yeah. So I don't go through Bazel. I just do it like with the compiled binary. And I think one of the issues is that LLVM MLIR has a lot of indirection, both for dispatch of like program logic and also for data structures. So most of the time, your debugger will be staring, like your debugger variable window will be a bunch of hard to interpret, like pointer to impl, like trees that are not really, like, I don't know if anybody has ever written like pretty printing scripts for GDB or LLDB for that. So it's somewhat limited because it's not as nice as stepping through like a more sane program where you actually get to see a lot of the locals. I mostly use it to see if code is even executed at all. I think that's like the best thing you can get out of the debugger is understanding where the control flow is going, which again, like it's sometimes non-trivial to figure out. We have done some amount of debug output for our own passes, right? And if you look at the pass, it will give you this, I guess it's not necessarily always pass name, but it should be. There is also things that aren't passes that have these debug only things. I think unfortunately the only way to find out about them is to like look at the source file. That might be a to-do for us to like, I don't know, in debug mode output like this information to like the docstring or something. I don't know, like because or just have this be part of the docstring for passes or for analysis, especially because I guess there's maybe less obvious what the debug type is. And yeah, I think we sometimes have a habit, at least I catch myself doing this, of adding a bunch of debug output while I'm working on something and then getting rid of it because it was like overly specific and not really putting in sort of like user-focused debugging code. So maybe if you run into something that you can't debug properly, feel free to yell at us on Discord, and we can also maybe add some useful debug information to a pass, because I think sometimes in order to understand why a pass isn't doing what you want it to do, you do need to understand quite a bit about the pass implementation. And so maybe rather than just sort of trying to reverse engineer an entire pass and doing your own debug output, just yell at the pass author to add the debug output they should have added.
Yeah, I think the fastest way to get help is probably to post something in Discord, and then like I think we're pretty good about like taking issues that people have and trying to systematize them into like longer term fixes. But then those longer term fixes end up being like something that you need to know exists in order to use it. So like we don't have a ton of discoverability at the moment, especially since it's kind of split between stuff that MLIR provides upstream and stuff that we do in our project.
So in for IR debugging, you mentioned that like you could visualize the graph using the graph viz if the IR is small enough. Like what if the IR is like what if the graph is large? Like what do you use then? Or it's just like, you know, try and
I mean, okay, I think the first thing is try to make your like failing example as small as possible. I think that's just generally good debugging like use. The other thing is that sometimes you will only see issues after a certain size. Like this was definitely true for me, like building some of the HEIR like vectorizer things where just you have to sort of go above the next power of 2 or something for like a failure to occur. Yes, MLIR reduce is a good point, but if it works, which is a big if, there is also some upstream MLIR debugging tools that I think don't necessarily work out of the box with like downstream things. So for example, like the built-in visualization to .viz is very, very naive in some sense, but there is like a more interactive visualizer for MLIR that was presented at Euro LLVM developer meeting 1 or 2 iterations ago. I don't have the name off the top of my head, but I can find it out and add it to the Google Doc later. And that one, the issue with that one is in order for it to support custom dialects, you do have to give it like some sort of like stub for the custom dialect. But yeah, there are tools that sort of work for larger, like, you know, you can sort of like unfold and fold certain parts of the IR and stuff. And if there is significant interest, we can think about providing these stubs for our like most important dialects.
I think we also have like an LSP, don't we?
Oh yes, definitely. Yes.
I forget what it's called, MR LSP server, and we have the HEIR dialects registered. So like if you're just trying to go from like in an LSP, go from like MLIR statement to like the defining op of a particular SSA value, I think that supports that.
Okay. Okay, the reason I ask is like, I mean, I'm a little less familiar with the compiler stuff, and so I ended up just converting an IR directly to what it runs on the hardware before realizing that, okay, I had to go and step back and do things in passes. But in my work, I had built in a lot of tools and kind of injections where you could not only like visualize things, but edit things along the fly, because I really needed heavy debugging. And now that I'm on this MLIR stuff and going through the standard compilation framework, like I'm looking for something like, okay, how do I debug things here? How do I visualize
Yeah.
things, or how do I inject things and edit things?
I mean, I think this is probably the
like,
easiest way to inject something is you can dump the entire pass pipeline that will run, print the IR at each step, and then you can go in and take the IR that you want to change at that step, modify it, and then you can run the rest of the pass pipeline.
Okay. Yeah. Yeah. So no expectations. I'm just looking for all the tooling that is available out there.
Yeah. Yeah. There's a lot of stuff. Yeah, and I'm trying to get more involved in upstream to like improve some of these tools. Like I really want to use MLIR reduce like all the time. Like having a minimal reproducer is like a huge thing for me. But the tool just like doesn't work very well out of the box, and so I would love to spend some time to improve it a bit. Yeah. Okay, we're at time. So thanks everyone for coming. I will stop the recording.